Okay, so cylindrical dynamics. Well, we start by reminding of ourselves of cylindrical kinematics. So there's the velocity vectors and acceleration vectors in cylindrical coordinates. Now for dynamics, of course, we're going to be talking about forces, and we'll often find forces in the normal direction. So that's like that direction right there. But of course, if we're doing cylindrical dynamics, we're going to want to resolve those into components in the radial direction, which is this way, and in the theta hat direction, which is perpendicular to it, like that. So we're going to want r and theta components, and that means that, well, we're going to have a little bit of trig to do. There's a helpful angle here that we will learn a little bit about in this derivation. So this is the r hat direction, this is the theta hat direction. This might be the normal force. Now, the direction the particle is moving here will be the tangential direction. And there's an angle between the radial direction and the tangential direction, this angle right here, that we'll just represent with a little dot, and I want to derive a relationship for that. Now, in the limit of extremely small angles, this is alternate interior. These two lines will be parallel in the limit of small angles, and so this will also be the angle in question. And so now I'm just going to consider this little triangle here. Let me just blow it up over here. Something like that. And so this is this angle in question that I'm looking for. This is just the increase in r, so that's dr. And then this is a little bit of arc at the edge of this triangle. Well, the arc length formula says that a little element of arc is a radius times an angle. In this case, the angle is d theta, so this length here is r d theta. So now we could just use the tangent ratio. The tangent of this angle that we're looking for is r d theta dr. And we'll use a symbol now for that angle. I'll just call it psi, the psi angle. So it's r d theta all over dr. But since r is typically expressed in terms of theta, the way that we write that is r over dr d theta. Okay, so that's the radial tangential angle, and we may need that later on. Okay, so that's just a repeated page. Here's our first example in cylindrical dynamics. We have to start with the force diagram. So let's try this again. Draw the forces on here. Now, what we've got here is we've got like a little marble that's being pushed by this rotating rod, and the marble is constrained to ride up and down in this vertical shaft. It is vertical. We're looking at this from the side view, so there will be a gravitational force vector here. The marble is also going to experience a force from this rotating rod. That'll be a type of normal force. And then finally, brushing up against the side of the shaft, there'll be another normal force on the marble, and as drawn, it's against this side, so the normal force will be to the left. So these forces then are, we'll call this the normal force from the arm, the normal force from the shaft, and finally just the weight mg. Now we notice that because of the rotation here, we have theta and r information. So we're going to do cylindrical dynamics. That means that we're going to want to find force components that are in the r and theta direction. So r direction, the direction of increasing r, that's going this way. Radial direction's out here. So we'll find force components that way. And then perpendicular to that is the theta direction. So that is our coordinate system. Now, let's label that then. So this is the r hat direction, this is the theta hat direction. So we see that this arm force is just in the theta hat direction, so that's easy. These two forces are also going to have components in the theta hat direction. There'll be a gravity component in the negative theta direction. Now that's familiar inclined plane geometry. If that's theta, this is 90 minus theta, so this is also theta. So that's an mg cos theta component. That's easy. This normal force from the shaft also has a component in the negative theta hat direction. Because of alternate interior, we know that that angle is also theta, so this will be a sine theta component. So we set up our dynamics, sum of the theta forces. We've got positive normal arm, then we've got negative mg cos theta, then we've got negative normal shaft sine theta, and that's got to equal the mass times the theta acceleration. Next, in the radial direction, so let's see, we've got a component here from the shaft in the positive radial direction, and then we've got a gravity component here in the negative radial direction. So it's going to be normal shaft cos theta, that's positive radial force, minus mg sine theta, that's the mass, times the radial acceleration. So now we need to find our accelerations. In order to do that, we need to know something about r and theta, so we can do kinematics. We see there's a triangle here, and this distance here is going to be r. Just let me recopy that triangle here. So this is r, this is theta. This is constrained to be 4, because that's a given distance. And the shaft is always going to be 4 meters away from this origin point, which is where the rotating rod is fixed. So we see that cos theta is 4 over r, or r is 4 secant theta. Now that'll be the basis for doing our kinematics. So we can enter that in here. R is 4 secant theta. We're told that the rod is rotating at a constant rate, and theta dot is given as 0.05. It's not changing. If it's not changing, then theta double dot is 0, so that mercifully makes that a little easier. And we could integrate backwards if we needed to and just find that this is 0.05 t. On the r side, we'll have quite a bit more work to do. We've got to do a ddt of 4 secant theta. Well, the 4 comes out, the derivative of secant is secant tan, but of course we have to multiply that according to the chain rule by d theta dt at the end. Now d theta dt is just theta dot is 0.05, so that's a constant. 4 times 0.05 is 0.02 secant tan. Now, in the question, the angle of interest is given as 30 degrees or pi over 6. So we can put in 30 degrees or pi over 6 here, and maybe we'll do that in a different color just for emphasis. So at 30 degrees, if you put in pi over 6, you get 4.619 for the radius. Again, at 30 degrees or pi over 6, this expression gives us 0.13 repeating. So now let's just return back to our calculation, because we have to do another derivative now to get r double dot. So that's going to be the time derivative of this. So we'll pull out the 0.02. Then we're going to have to do the product rule here. So we'll keep secant by itself. Then we'll do the derivative of tan, which is secant squared. And then, of course, we've got the chain rule. We have to do d theta dt. Then there's going to be a second term, which will be 0.02. Keep the tangent, and then do the derivative of secant. Well, that's secant theta tan theta, again, d theta dt. So we end up with 0.02 times 0.05. Oh, sorry, no, there's a mistake back here. 4 times 0.05 is, let's correct this, is just 0.2. Yeah, my values are getting too small here. So that's just 0.2. So this is just 0.2. I guess I'm going to have to rewrite it here. Okay, so 0.2, 0.2. All right, so now when we do 0.2 times 0.05, which is d theta dt, all of these terms end up with a 0.01 in front of it. Then we have secant cubed theta plus secant times tan squared theta. So that's the expression for r double dot, which is the time derivative of this, subject to theta dot being a constant value. Now, if you put in 30 degrees here, at 30 degrees or pi over 6, this works out to 0.0192. Now we can take those values and we can do our kinematics, because here is the expression for the radial acceleration. And so we've got to put in r double dot, and so this is the radial acceleration here. So r double dot was 0.0192 minus the r value, that was 4.619. Theta dot squared was 0.05 squared, and so we get 0.00765525 for the radial acceleration. This is the theta acceleration here, and r, because theta double dot 0, that term just disappears, so it's plus 2 times r dot times theta dot, and that's 0.013 repeating. And both of those are in meters per second squared units. So now that we've done our kinematics, we're now in a position to calculate our forces. So the angle of interest was 30 degrees. So we could substitute in 30 for the angle, 9.81 for the gravity field, the mass of 5 kilograms, and then this radial acceleration that we just calculated, 0.00765, and then you can solve for the normal force from the shaft. I get 28.36 newtons. Then you can take that value and put it into this equation, and once again, the angle of interest is 30 degrees. The mass is 5 kilograms, and then the theta acceleration was 0.013 repeating, and then you could solve the normal force on the arm, and I get 14.18 newtons. So that's a problem in, you could say, elementary cylindrical dynamics, but obviously we had to work pretty hard to get the kinematics there with all the time derivatives. Here's another problem. Let's try this one next. So we'll start with a force diagram. So here we've got in top view, so we won't have to worry about gravity because it'll be into the page in the binormal direction or the z direction. And here we've got a slider. Again, it's being pushed. Oops, sorry about that. It's being pushed. It's pushing a little marble along here, and so there'll be a normal force from this arm in that direction. And then the little marble is brushing up against the track, so there'll be a little normal force there, just like that. And those will be the two forces that act on it. Now, perhaps, should I move this one? Yeah, maybe I'll move it in there like that. There we go. And it's frictionless, there's no friction, and weights into the page, so that's all the forces. Now, before we leave the line drawing, maybe I should just add in my coordinate system. We're going to resolve this into force components in the radial direction. So this will be radial here, direction of increasing r, make it a little smaller, and then perpendicular to that will be the direction of increasing theta. That's the theta hat direction. So that then leads to the following. Oh, would you stop with the email? Leads to the following. Just turn off wireless so I don't get any more of those emails. There we go. So this is the radial direction, this is the theta direction. So we said this is the normal force from the, let's see, the slider, a rod. And then this is the normal force from the track here, which is a groove. Okay, so now, once again, we see this is just in the theta direction, so that's pretty easy. But over here, the particle's moving this way, so this is the tangential direction. We see that this force is in the normal direction, so we're going to need that radial tangential angle psi here. And then this will be the complement of psi, and then this will be psi. And so we're going to have, for this normal groove force, we're going to have a component that's in the theta hat direction, positive, and then we're going to have a component that's in the negative radial direction. So that means we've got to break out that relationship from earlier, which said tan psi was r over dr d theta. Now the shape of this groove, r is 1 plus 2 theta, so that's pretty easy to differentiate. So we substitute in r as 1 plus 2 theta. dr d theta just gives us 2. Now the angle of interest is pi over 4, so we put in pi over 4 here. Divide by 2. This is tan psi. Now this is just a number, so we can do the arctan, and we find that the angle is 52.12 degrees when theta is pi over 4. So we could use that 52-degree angle now to get components of the normal force. So let's do our dynamics now. Let's write our force equations. So the sum of the forces in the radial direction first, well, there's only one. It's just this component of the groove force, and it's in the negative radial direction. So this is going to be minus normal groove, and this is the sine psi component, and that's going to equal the mass times the r acceleration. And then in the theta direction, we've got the normal force from the rod, and then also in the positive direction, we've got a component of the normal groove, cos psi. That's the mass times the theta acceleration. All right, now all right, so once again, now we need to do kinematics. So we just pull in our r value here. It was just 1 plus 2 theta. Now at the angle of pi over 4, if you put that in, you can work up the r value. Theta dot was 0.2. That was a constant again. Our kinematics is going to be a lot easier this time. The derivative of that's going to be 0, so if you integrate backwards, you could show that's your angle as a function of time. If you do a time derivative here of 1 plus twice theta, you just end up with twice theta dot. So that's just 0.4, and that's a constant. And so the second time derivative, or the ddt of that's just 0. Putting in the value of pi over 4, you find that the r value is just 2.571. So now we can do our kinematics here. Substituting in, we get for the radial acceleration here a value of minus 0.1028, and then substituting in for the theta acceleration, both of these terms are just 0, so this is r theta dot squared. So that was just the 2.571 times 0.2 squared gives this. And then here it's just 2 times r dot times theta dot, so it's just 2 times that one, and that gives a value of 0.16. So now we substitute those into our dynamics equations, and then we can calculate the unknown forces. So minus normal groove sine of the 52.12 psi angle is the mass, which is 1.2 kilograms, times the radial acceleration of 0.1028. So this gives a normal force in the groove that's actually negative. And the physical interpretation of that is just that I had drawn the marble touching this side of the track. Really, the marble should be touching this side, and the normal force in the groove should be pointed in the opposite direction. So it was just a bit of a guess. There's no harm done. That's my interpretation there. Just I got the wrong direction. So substituting that in there, and the 52.12 degree angle, the mass once again, and now the theta acceleration, which was 0.16, I find the normal force from the rod to be 0.315 newtons. And that completes our 2 examples in cylindrical dynamics.